Hello everyone, my name is Firas Shari, I'm CWNE 348. Today we're going to be talking about OFDM, the difference between OFDM and OFDMA as a part of this fourth video on the 802.11ax training. So OFDM is not a new concept in Wi-Fi. It has been introduced in 802.11a. OFDMA, however, is a bit of a new concept. It has only been introduced with 802.11ax. So what's the difference? OFDM is a modulation technique. Basically, what you do is you have a chunk of bandwidth, you divide that into some number of orthogonal subcarriers, and then you load your data on those, and then you send them. But the problem is, like, OFDM will only allow you to assign all of those subcarriers to one client at the time, and this is how we have been doing things in Wi-Fi for a very long time. We use CSMA to access the channel, and then we assign the whole channel and the whole number of subcarriers to a certain or to one specific client. Now with the introduction of OFDMA, the game is different. So now OFDMA as an axis is the channel access method. It allows you to divide those subcarriers, the number of subcarriers you have, into subgroups, and you can assign each subgroup to a different client, so you can have multiple clients that can access the channel at the same time. Okay, so does that mean like we don't do CSMA anymore? No, we still have legacy clients that we have to notify and tell them that hey, we're going to be using the channel. So what usually happens is the AB uses CSMA first, content for the channel. It reserves the channel, reserve the medium, and then uses set up an OFDMA, whether it's an uplink or a downlink transmission for multiple clients to participate in. OFDM is more helpful when you have like a smaller loads. If you have more of latency and jitter sensitive applications, where you can have multiple clients participating in the same transmission at the same time. The OFDMA in Wi-Fi is a bit different from OFDMA in cellular networks. Since OFDMA as a concept is not a new, it's not a new thing. Like it has been around for quite some time. It has been part of the the 4G networks, the LTE, now recently the 5G networks. So it is not a new concept, but it is a new addition to Wi-Fi. But it is a bit different the way it operates in cellular networks comparing to Wi-Fi networks. So in cellular networks, it's mostly time based. So you have your network where the network will decide, okay, they're gonna be a time interval here where those numbers of clients or all those clients will participate in an uplink transmission or a downlink transmission, right? In Wi-Fi, it's frame based. So the AP will decide on a frame basis whether to use OFDMA or not, and that decision is taken by the scheduler. The scheduler, job is to decide whether to use OFDMA or any other like multi-user access techniques on a frame basis. So it takes into account the number of clients, their RSSIs, their capabilities, the loads, frame sizes, and packet sizes, and many other inputs that the algorithms will crunch and will decide based on that whether to use OFDMA or not. If we see here, this is actually taken from an actual OFDMA transmission between an AB and two 80 megahertz clients. So in the first two screenshots on the upper part of the the slide, we can see the two clients are actually sharing the 80 megahertz bandwidth that is being divided into two RUs. So we have actually one client that's occupying the first 40, and we have the second client that occupying the second 40. We actually did this by using two spectrum analyzer. Each one of them was connected to the actual antenna port through a coupler. This wasn't a conductive testing. If we can see here, like the difference between the two screenshots in the upper picture and the two in the lower picture is that we're using OFDMA in the upper picture, so it's like both clients are sharing the channel 100% of the time, but the bandwidth is divided between them. If we look down to the other screenshots where we're not using OFDMA, each one of the clients occupying the channel, occupying 100% of the bandwidth, but is only occupying actually the channel 50% of the time. So whether you're dividing on frequency or dividing in time, like, theoretically you should get the same results, but we know, like, from in a practical protocol like Wi-Fi, all the management overhead that comes with whether you're dividing on time or divide on frequency, this is what decides how efficient you are, and how much airtime you're going to use or how much throughput you're going to achieve by dividing whether either on time or dividing on in frequency. I mean, it's a still picture, so you can't really see it here, but the assignment, like for the the chunk of bandwidth, the RU here, it's not a fixed one. So one client could be assigned the first 40 and the 80 megahertz channel, and the next transmission it will be assigned the next 20. So it doesn't really it's not a really a fixed assignment. It could change. The AB could decide which chunk of bandwidth you would be assigned to on a frame basis. Like your assignment could change every on each frame. Okay, so those chunk of bandwidth are called RUs. So in the standard, the RUs are predefined. There are, like, you can't just like assign a random number, a random like chunk of bandwidth to a client. So the AB cannot say, okay, I'm gonna assign to the first client like 13.75 megahertz of chunk of bandwidth. Like this doesn't work. So in the standard, there are like a predefined chunk of bandwidth that has been labeled RUs, radio units, radio resource units, and the AB can choose each one of them. Depends on, like, the number of clients, the traffic load, the channel bandwidth, many other parameters. But the AB will choose one of them to assign to each client participating on an OFDMA transmission, whether that is an uplink or a downlink. If we look here, we can see the RU allocation for a 20 megahertz channel. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 of the 26 RU. So a 26 RU is a 2 megahertz chunk of bandwidth that actually has 26 subcarriers. So that number means the number of subcarriers inside that RU. If we look at here, we have, if we combine a 226 RUs, we get the 52, and that's a 4 megahertz chunk of bandwidth that has 52 clients, and then 52 subcarriers. Then if we combine two of them, we could get the 106, which almost like a 10 megahertz chunk of bandwidth. And then the whole channel, the whole channel, the whole 20 megahertz channel can be used as one RU, which called the 242. If we see here, like, even after like combining like the 26 here and getting like the 552, we still have 126 RU in the middle of the channel. So like if you count the RUs here, you have 1, 2, 3, 4, 52 RUs and 126 RU in the middle. Okay, if we jump here to the 40 megahertz, so the 40 megahertz basically just a replication of two. It's just a replication of two 20s. So this is your first 20, and this is your second 20. As you can see here, the channel can be either divided to, like, all 26s, 25, 20, couple of 52s with couple of 26 in the middle, and or like a 106, or it can be divided into two full 20 megahertz RUs. Likewise for the 80 megahertz, it's just too big to be one continuous graph, so it has been like truncated here, and the rest of it is like under it. But the whole thing, this is like what a whole full 80 will look like, and it's exactly the same thing. It's either like you can look at it as a 240 or like 420s. You can still see the same RU's allocation inside the 80s. Likewise, the same thing goes for like 160. 160 is just two 80s, or it can be you know 820s, right? Okay, so if you look at this table here, we can see that the 26 subcarriers are used. Like in a 20 megahertz channel, we have 9. In a 40, we have 18. In an 80, we have 37 of them. In a 160 or 80 plus 80, we had 74. Okay, so if we go down here, we can see the predefined RUs. And each one, and how many subcarriers does each one of them have. So if you look at the 242, this one is an equivalent to 20 megahertz channel. So under the channel 20 megahertz channel, it's only one RU, and this is the case where we're actually doing single user MIMO. So we're sending all your spatial streams to one client. So with that, the full bandwidth. Or we could be doing actually multi-user MIMO at the same time, where we have the same bandwidth. We just use assign each client the full bandwidth, but we divide the number of the spatial streams to different clients. Likewise for like 40, like if you look at the 40s, you can see how many, like 26, 20, 52, 106, and of course it has only 242 and only 140. And the same thing goes for the rest of the mapping. Thank you very much. This concludes our video for today. The next video, we will be talking about OFDMA in action, how the ABE sets an uplink OFDMA and a downlink OFDMA, and we'll look at some trigger frames, packet captures that kind of clarify the concept. Thank you very much.